So welcome to the spring 2019 semester the semester of data mining. So I assume all of you are in the right room. This is a large room. I guess this class has grown a little bit since last year. So that's exciting. We'll get to hear about lots of cool stuff, and you all are going to work on projects in this course. And so this means you get to do a kind of a distributed kind of search over the space of cool projects you can do, and you'll all get to see what everyone else is working. So I think having a large class would be great. So I'm Jeff Phillips. So I'm the instructor for this course. I've taught this course. I think this is about the 8th time I've taught the course. The first time I taught it, it was only like 30 students, and it's grown just about every year. So we also have some great TAs for the course. Let me zoom in on this just a little bit here. So two of the TAs are here today. So one is Madia. You can raise your hand so everyone can see you. So he was all the TAs were in this class last year and excelled in the class, so they should be able to help with questions. Another TA who's here another TA who's here is Bonin, who's in the back, right? And then Harshini and Garima are still traveling and won't be here, I think, until the end of this week or the first part of next week. So that shouldn't, usually there's not too much going on the first week. I think that should be fine. When they get here, I'll have them come and introduce themselves as well. We've started to post some possible times for office hours in the class. So my main office hours will be 10 to 11 every morning on Thursday. And then also, I've blocked off the time directly after this class. So this is a great time to ask me questions, anything from kind of general questions about data mining to things about the project to technical questions about the lecture or the homework. And if another class comes in here, then we can walk back to my office and have more time afterwards, okay? So I think this is the easiest time when that doesn't interfere with most of your schedules as well. The TAs, I think we're probably pretty close to our final proposition for the office hours of the TAs. You'll notice that there are going to be 4.5 hours of office hours on Tuesdays. So that's because the homeworks and all the assignments will basically be due on Wednesdays, and so they'll be due Wednesdays before the start of class. And I kind of know how it works, that probably most of you will wait until the last day or two to actually work on the homework assignments. So and usually the most need for them are the day before, so we've loaded a lot of office hours on Tuesdays. Okay? If for some reason you're looking at this now and you're saying, I can't make any of those times, and I get more than, say, one person saying this, even if I get one, we'll try and see what we can do to rearrange these times. But I don't want to hear, like, at the end of the semester, well, I could make any of the office hour times. So if there's a major conflict with known classes, then please let me know. You can send me email as well if you don't want to say it right now. But please do this within the next week or two as you're figuring out your schedules. And then we may, and one option would be to have like some online hours as, some online hours as well, where they aren't in one of the offices. But we'll try and work to be flexible with this. If things are not working out later in the semester, we might be able to shift things around later. We'll see how things go once you have the first few homework assignments as well. But if this isn't working out, if you don't tell me that, then I don't know it needs to be fixed. So great. So the next thing is that this class is going to be recorded, and so you see Madia up here in front with with the camcorder. We're upgrading the equipment we're using to do this recording. So for the first week, we're not going to be live streaming the class, but afterwards, the plan is to live stream all the lectures on YouTube. And you can follow the links right here on the page to get to the live stream, and then all the videos will appear up there as well. These videos should appear sometime later today or tomorrow, after they're being recorded today. So even though I'm recording these lectures and you can just watch them online, I highly recommend you try and come to class. Or if you can't come to class because you have conflicts at this time or you're working, at least try and watch the lectures as you go, or live if you can, and if you can't do that. It is the people who are in class and participating do much better in the class than those who don't. Okay, this is a pattern I see every semester. I'm putting the lectures online for your aides so you can review stuff and so you can be more flexible in getting lectures. But you should not think of this as mean you don't need to come or listen to lectures. You might be able to do okay on the homeworks and so forth, but you're not going to get as much out of the class. If your goal is to learn a lot of material here and to do really well, you should really try and come to the lectures. I think it's an important part of the class. There's a lot of there'll be a lot of mathematical notation and so forth, which is the language used to describe the algorithms and the analysis used in data mining. And in class, I will explain these things carefully, and you'll get a chance to ask questions if you don't understand it. It's all going to be in the notes, and you can read it, but it'll be harder to understand. I think the experience has been students have found it hard to understand if they're not kind of seeing it developed in front of them. Okay? So try and come to the lectures, and if you can't come to the lectures, try and watch them as they go. If you start falling behind, you're gonna fall further and further behind. So the next thing I want to point out is the books and the notes of this class. So if you look down at the schedule, and I'll kind of talk through what's going to be on the schedule, you kind of see in this column here are going to be the notes which are going to fairly closely follow what's actually in the lectures. So I've developed these notes over a number of years, and they basically are like, think of scribes of my lectures written down more formally. Okay, so kind of these will follow fairly close to what I'm going to lecture here. They'll describe the notation. You can click on these, and it takes you to kind of fairly detailed notes of like what's going on. Okay, so you can follow you can kind of see and get the explanations here, and this will follow fairly close what's in the lecture. But there also is so there's also a book I've been working on, which is this Mathematical Foundations of Data Analysis. And this has mainly been built around a previous class I taught that was mainly for undergraduates, which is basically this, I think this semester or last fall is called CS so 3190. And so those lecture notes I've turned into a book, but I've expanded it recently, and so it will now cover a lot of the stuff in the data mining class as well. And you can click to get the most updated version of the book. I don't think probably won't update this during the semester, but this is so version 0.4, and let's see, this book is, yeah, so this book is like, it's much more detailed and probably nicely written with more examples clearly defined than the lecture notes I have for each lecture. But it does not exactly cover everything in those lectures. I haven't put everything from the lectures in this class into the book. Okay, so if it's in both, I would recommend looking at the book, but it won't always be in both. Okay, and so there's be much more detail in the book. Okay, so, and I tried to, you can see for this locality sense of hashing, this corresponds with in the book Math for Data Analysis, chapter 4.6. Right, so you can kind of see where it is in the book. Okay? So I think there should be a lot of, at this point, fairly good resources for the class. It's not a single published book that covers everything, but it's working towards that. I've also given notes to a few other sources. There are a couple of other books which are also free online. There's this, so there's this Mining Massive Dataset book and this Foundations of Data Science book. I find the Mining Massive Datasets book is a bit more kind of from like a databasey sort of perspective. It's a bit more applied and not kind of the way they cover the mathematical part. I think is not as complete as I do in this class. And then the Foundations of Data Science book is on the other end of the spectrum. So this book is basically just the mathematics of like what's going on. It does a great job of covering those topics, but it's not as covering necessarily the practical elements of it. So this course will try and blend these two things together. Have you understand the foundational mathematical principles and notation behind everything, but also try and inform you, okay, here's kind of mathematically why it's going on, but here's what you actually do and what's commonly used to get this to work in practice. And here's when this technique works, and here's when this other one technique works. Right? So we're going to try and split the difference between these two things, and that's what, and that's why neither of these two textbooks, I think, from my view, are like the perfect fit for the course. But I think between the 3 or 4 of these sources, there's going to be a lot of resources. Okay, and they're all online. They're all free. Okay. So the prerequisites for this course. So this course. I mean, all of you students in here come from a wide variety of backgrounds. I haven't looked up the exact breakdown this year, but usually it's about 2/3 to 3/4 of the class are somehow in the School of Computing, either as a computer science degree, as an undergraduate or master's or a PhD degree. But another 1/4 to 1/3 are from, you could be a non-matriculated student, you might be in the physics or in the math department. It's a sizable part of the class. Now, I'll kind of expect that everyone has a background. Hopefully, I've told this to a lot of you and it's on here, but I expect most of you to have some background in programming. So I'm going to ask for assignments. We're going to talk about these algorithms and techniques. I'm going to say, okay, now go and implement this in the assignment. And I'm not going to give you too much hand-holding in, okay, here's the basic class wrapper, and you need to kind of write these lines of code and then run this. I'm going to say, here's the data set, or here's how I want you to kind of simulate this randomized approach, and then go ahead and do it. Okay, and you can use any language you want to do that in. Often the more powerful languages are going to be easier to do it with, right? So your C++, Java, and especially Python makes these things especially easy. Students have gotten by just using like R, but this is more rare, okay? These are people who's like, I program R all day long, I'm really good, and they get it to work. But there have been assignments where I heard them in the beginning of class discussing, someone did it in R, he said, I ran this question, it took me 24 hours to run. Someone else wrote it in Java or something. He's like, oh yeah, mine finished in like roughly a second. Right? So, you know, and now maybe some of that was like, okay, they didn't program it right, but like these high-level languages like Java and Python give you kind of the right framework and setup to do things efficiently. And sometimes that becomes hard to doing stuff in R or in MATLAB. I think I've made the sizes so you can, of the homework assignments, so you'll be able to see the difference. but you'll be able to finish it if you are going to use something like R. Okay, but it'll just be kind of painful. Okay, but it shouldn't be too bad if you're using. It might take. Sometimes something might take an hour to run, even if you program it very well, and that's fine. That's the nature of the problems. All right. So expect some programming. If you don't have as much, you can learn some as you go. That might be okay, but you'll learn more without that being a barrier to your learning. I hope that's not. You're not taking this class to learn how to program. Okay, that way you'd be focusing on that instead of learning everything else. All right, so the other kind of important things I'm expecting are some familiarity with concepts in probability. If I say kind of like what is an expected value of something, or I say kind of just write something, the probability of a statement, that this is not a foreign idea to you. Okay, in the second lecture, the next lecture, we're going to kind of very rapidly go through some properties on kind of some basic statistical principles around the ideas of how to think about things like the central limit theorem. And hopefully this is kind of somewhat of a refresher for most of you, but it'll be in a different perspective unless you've taken the 3190 course. Okay, so it'll be probably a fresh perspective on those things, but hopefully the ideas of expected value and probability are not foreign to you. Okay, there won't be too many specific things you need to know about different distributions and statistical testing and stuff like that. But the basic ideas, if they're not familiar to you, this stuff is probably going to go over your head pretty quickly. Okay, and then probably the most important thing that is that you have some exposure to the ideas of linear algebra. Okay, so a lot of the language we'll use to describe how the algorithms work, how the data is presented, how to kind of like abstractly talk about data will be through linear algebra. Okay, so there's some plug up here. Now, what specifically do you need from linear algebra? I mean, you need to know what a vector is, you need to know what a matrix is, how to add vectors and matrices and multiply them. I'll review these things quickly in the course. If we'll spend in the section on when we talk about regression and slow dimensionality reduction, we'll talk about the about how to use the the singular value decomposition for data analysis. So who knows what the singular value decomposition is, and who's not heard of it before? All right. Okay. So we will review it, what it is, and in one lecture, when I think it should be done over 2 or 3 lectures if you haven't seen it before. So luckily, the course notes in the book, I spend that much time doing it. We'll just go through it really quickly in the class, and then we'll spend another lecture or two on the how to use it in various ways. All right. So like that's the sort of thing that would be useful to know from a linear algebra course. If you're familiar with the basic idea of matrix decompositions and multiplication, you should be able to pick this up well. But some of these things are things that I'm teaching you as well, how to interpret it from a data analysis perspective. Okay, so you don't need to know everything there is about linear algebra and how to think of it in all these ways. That's what I'll be teaching you, but if you haven't had any exposure, it's going to go really fast, and you're probably going to get a little bit lost. Okay? So, okay. I'm trying to accommodate people with lots of different backgrounds in this class, so how that'll be is some points I'll review something that some of you will have seen before, but I'll go through quickly and hopefully give a new perspective. And a lot of the rest of the time I'll be saying, okay, let's talk at these advanced techniques and kind of analysis, kind of getting closer to kind of the what is the cutting edge of like in these different areas. Okay. Okay, one more thing I want to point out is the basic syllabus for the class. It's going to be linked off of here, right on the web page. Okay, and so you should go through and read what's in the syllabus. This is basically my contract to you, the class, about how we will teach it, how I will be fair about, various things that, which I should be fair about. So kind of what's on the course webpage, kind of reviewing what the prerequisites are, kind of the basic policy on the grading in the course. So 45% will be on the homework assignments, 45% will be in the project, and 10% will be these would be the 2 tests. So each test will be 5%. So the tests don't count that much of the grade, but those probably people tend to get further from 100% on them. Okay. So and the grade mapping will probably be, it's usually in the basic range. I give myself the flexibility to curve up. So if everyone in the class does poorly, I could make this a little bit easier for you. But I don't plan to say give a B+ to someone who has a 92%. Okay, so if you get above 90%, you're going to get at least A-. Okay, so it's a good thing just to keep in mind. Okay, the homework assignments, there is a late policy on them. You can turn them in late if you want to. If you turn them in up to 24 hours late, you will lose between like 1 minute, or actually 6 minutes, and 24 hours late, you're going to lose 10% of the points. If you turn it in between 24 and 48 hours late, you can lose 20% of the points. After that, I won't accept it anymore. Okay, so you can turn it in late if you need to, but you will lose some points. Okay, and all the homeworks will be turned in through Canvas. Those are timestamped. They're all, except maybe the last one, are due at 2:45 p.m. on Wednesday. So you have 15. After you finish it, you have 15 minutes to get here to class. I want you to still come to class, even if there's an assignment due. And Canvas will have a late check-in at 2:50. Okay, so it's due at 2:45. I'm already giving you a 5-minute slack window. Okay? So, but if Canvas marks it as late, it's late. That's the policy. Okay? So that's that. That's the late policy. If you believe there's an error in grading anything on a test or homework or something, you have, from when you get the grade back, you have 1 week to tell me. And then I will carefully look at it if it's the case. In a large class, this is bound to happen. Don't feel afraid to kind of, if something's misgraded, please let me know. It should be done in email so I can keep track of it. Okay, if you come up to me after class, I may not remember it because there's a lot going on. If you send me email, I will check the email. Okay, and it will be a record that will be within 1 week, so there will be a hard record of it. All right, so, in general on the homeworks, I encourage you to work together on them, but you should write up your own solutions, you should write your own code, this standard sort of thing. Right? Otherwise, you're not going to learn. This is for your own good, right? So if I catch you cheating, unfortunately there are consequences of cheating if you're doing more than just kind of working together on it. But you should write up your own stuff. Okay? And on tests, they'll be in here. If I catch you talking during the test, if me or one of the T's is not present, I will take the test from you and it's going to get a 0. Okay. That's just the only way to get this to work for a large class for me, at least. So it hasn't happened yet, but once I had this policy, it kind of cut down on possibly bad chatter. So it seems to be working. Okay, and then the standard stuff, students with disabilities, talk to CDS. If there's issues with misconduct, these are the standard policies of the School of Computing. I encourage you to use LaTeX in writing up the homework. On Canvas, you will be turning things in as a single PDF for each homework assignment. Okay, you probably won't need to turn in code. Sometimes I've occasionally said, okay, this assignment, I'll require you to turn in code and I'll let you know a week before it's due. But generally I won't ask for code. I structure the assignments so that I can actually tell if you're running this independently of someone else or if you've written it yourself pretty much without looking at your code. There are going to be these randomized algorithms that you run and everyone will have their own randomness. And you say, oh, it was random, it did something crazy, you should count it. No. It's like randomness is controlled if you do it enough times. And I and the TAs know what it's supposed to look like, so we'll be able to grade it and we'll be able to tell that you didn't just completely copy something from someone else. So it generally be a single PDF to Canvas. I recommend LaTeX because it's the language that all the papers and in this area are written in this. If you really don't want to do it, you can, as long as it's legible, it's fine. Okay, but if it's not legible, then we have the right to mark off on the assignments. Okay, look, Word has actually gotten a lot better the last few years about being able to write in mathematics in Word. I'm not that familiar with it, but if you want to go that way, that's fine as well. Okay, but kind of LaTeX has a little bit of a learning curve at the beginning, but it's also gotten easier with things like, I don't recommend overleaf, although it makes it pretty easy to do. I will give the source LaTeX that the assignments is written in, posted online as well. I did this for the first assignment already. So it gives you a starting place to work. Okay. Any questions on the syllabus so far? Okay, so feel free to ask questions during class, please. I assume once we start getting to technical stuff, some people should be asking questions. It doesn't need to be you necessarily, but if no one's asking questions, then if you realize no one's asking questions, it probably should be you. Okay, so that's generally how it works. So it probably means you have a question, and you should ask. All right. So let's look at the schedule a bit more. So I'll link to the videos in this column here once they're up on YouTube. There'll also be a YouTube channel and playlist you can find them on. All the assignments will be in this column, and the project due dates will be in this column. And I've tried to set up the schedule so that most Wednesdays there's going to be something due. Okay, so and I changed this a little bit from last few times I've taught this, and that there are more number of assignments this semester than in the past, but I've taken some of the bigger ones and I've split them into two. Okay, so I think this will be more evenly spaced out than it has been in the past. For instance, this used to be a single assignment. I've split it up into two due dates instead. And I'm moving some stuff around. They're not always exactly the same. Okay, so and so the first homework assignment is due on next week, Wednesday. So I've posted, how many people saw that post on Canvas where I updated it just this afternoon? Okay. So I've linked off the PDF off of Canvas, and you can also click here and it should also get to the assignment. Okay? And so they'll be posted in the spot when they're due, and my goal is to get them up at least 2 weeks before everyone is due. Every assignment is due. I think I should have them up in at least that time, except for the first one. It's due in less than 2 weeks already. Okay. All right, but that should be that should be the pattern going forward. So you should have at least 2 weeks to do them, even if they're spaced every week apart. Okay. Also, you can notice that there are going to be 8 total assignments, but there are going to be 5 before spring break, and then only 3 after, with 1 due kind of basically after the semester ends. Okay, the reason for this is so there are really only 2 assignments, and this used to be 1 assignment that I've split, that's due after spring break, because you should be working on your project much more at this period. Okay, so it's kind of front-loaded in terms of the homework assignment, and then the project itself the final report will be due on April 15th only, right? The semester ends kind of like at the end of April. The final report will be due earlier. That's because you're also going to make posters and have a big poster presentation. So the final exam slot I will use for a poster presentation. I believe this is okay according to the guidelines of the exams, although I may have to extend the amount of time so I can see all the posters. There'll probably be about 60 posters this year, so it'll be a long day for me. But a very fun day, but I'll be tired of it. So okay, and we need to finish the posters so we have time. We'll print them. The school computing will print the posters for you, and then in one of the MEB hallways, we'll fill up 2 full hallways full of posters. So it should be pretty cool. Okay, but the second half of the semester, you'll be much more on the project, and it's harder to do that earlier on because you haven't learned all the techniques from class yet, right? So you'll be working out and working through the techniques early on, and then you'll be able to apply them on the poster in the project later on. Okay, but still the project is going to have some intermediate due dates. Already in 2 weeks from Wednesday, you're going to turn in a proposal of your project. Okay? If you click on here, you'll see. If you click on there, there's a document, like a 6-page document, overviewing what's going to go on in this project. And the first thing is January 23rd. You're going to turn in a proposal. This should be short. Okay, it should be 1 to 200 words. The important thing is I want you to kind of pick an area to kind of try and start thinking about, and also to form a group. Groups will be of 2 or 3 people. Bigger than 3, I think there's almost always at least 1 slacker in the group. And if it's less than that, then I'm not going to be able to handle that many projects, right? So, there'll be some limited exceptions, like if you're doing some research project that you've been your thesis is on this, and some element of it would work really well as a class project. I will grant some exceptions for this, but this needs to be in writing in email. Okay? So you need to email me to get approval before the proposal is turned in, otherwise you'll lose points on the proposal. I think the proposal is worth 5 out of 100 points, and you would lose some of those points. Okay, so, and if you don't have a group of 2 or 3, you will also lose points. So that's kind of what you need to be working for, is trying to think of some topic and trying to come up with a group of like-minded people. Okay, so what are good projects? What are good kind of topics to work on? I've got a bunch of posters, some of the better posters from past years. I'll bring them in to class, I think starting on Wednesday, so before and after class you can come look at those to get ideas. Another way is to I've listed a bunch of places with some links to some data sets. And you can just look at those data sets and say, hey, I wonder if I could apply this technique or that technique onto these data sets. These are good places to start thinking of now. Another thing is you look at some technique that you look on the webpage, say this looks really interesting, I want to somehow work on this technique. I'll try and figure out what the data set is I'm going to run on later. That's also okay at the time of the proposal. What works best, the coolest projects are when you bring some cool passion that you have outside of the course. right? So one year someone was like to go hang gliding. Okay, so he would, if you ever see those hang gliders jumping off some of the mountains, and then they kind of circle on down. And he found that someone had been collecting data of GPS traces of people hang gliding. And so he tried to cluster, and if you know how to do it right, apparently, there are these thermals that will push you back up. And then you can keep going with only one climb up the mountain. And so you want to try and cluster the thermals, right, using all these GPS traces from hang gliding. This was a cool project, right? So think of something that you have a passion about. Last year someone did something, he worked in a lab with some snails that ate other snails and other stuff. And he tried to look at, there were like 100 different types of these snails that he had information about. So he tried to kind of group together and learn something about how to build a network, or how to cluster, or how to predict stuff based on different properties of the snails, right? So these are kind of interesting projects. And I could not possibly suggest this to any of you. So I want you guys to come up with these things yourself. So if you have questions about would this make a good project, after class, before, a little bit before class, I'm usually trying to do stuff, but those are good times, or my office hours and so forth. Feel free to ask me. I've been doing this for 8 years now with these projects, and I'm pretty good at helping you hone projects. Okay. So the lead TA for the projects will be Madia, right? So he'll also he'll be reading through everything more carefully and checking stuff for me. So he may also be a good person to keep in the loop on some of these things. I'll work with him to sort through it and give you all advice. Okay, so as you know, it's a large class, and I want to give kind of as much kind of hands-on advice on these projects as I can. Otherwise, they tend not to turn out as well. Okay, and so I'll try and look through the proposals and the data collection report, which is the next intermediate step. And then at some point, right after spring break, you'll have some intermediate report, where in class you're going to break into groups and give each other feedback. And then in the next week after that, I'm going to schedule short meetings with all the groups, with me personally. They'll be pretty short, like 5 minutes or 7 minutes they were last year, but this is actually usually a good time. Some will take a little bit longer, some will take less time than that. But that'll give you a good checkpoint to see how well you're doing. So I want kind of the basics kind of outline. You should be sure of what you're doing and get some basic stuff working at this point, and then you'll have a few weeks to still refine this by the end of the semester. Yeah, so this is kind of the basic structure, how you can work on this throughout the semester and still get a pretty cool project. I think this class generates some of the best class projects in the school computing because of the structure I have. So try and follow along. Basically, in the grading of the project, it should not be hard to get basically 100%. Most of you, everyone should get 100% up to the intermediate report and on the poster. The final report, which is I think 40 or 150% of the grade, I will have some leeway of saying this one was clearly better than this other one, so I'll give it more points. Right? But you should be able to get a lot of these checkpoints done. Just there, you'll get points for completing what you should have done at this checkpoint. Okay. So, any questions generally on the structure of the project? We'll talk more about it as the deadlines come up. But yeah.
Is it going to be ranked? Are each of the posters going to be ranked? Is that
well,
how you're rating it?
Okay, so the posters is a different thing. The posters will actually, they will be ranked, but not by me. All of you will vote on the posters. And so, but the posters, so I will give you a grade based on the final report. That's the large chunk of the grade. The posters, you will get some like completion points, and then the best 2 or 3 posters will get some bonus points on top of that. And those will be, everyone will go around and get to vote on their favorite poster, whichever you think the best overall project according to the poster. You will vote on that, and the best people will get extra points. So, and this, I think, and you'll get to design the posters yourself. It'll be a lot of fun. Okay. So, but I'm not going to actually rank the final reports, but I'll kind of, as I read through them all, I will kind of grade them in buckets. Like 45%, like I think 45 out of 50 is you completed everything, but didn't go above and beyond anywhere, and something like that. So, and then I can give up to 50 points on the final report for people who truly went above and beyond and did just amazing projects. You know, if you just do what's required, you'll still get like 45 out of 50 points and say 95 out of 100 points on the project. You shouldn't complain about that. But, well, I can talk more about that as it gets closer. Okay. I want to encourage you, like this class, you can get by and just learn the basics in this class, and you can learn a lot more if you apply yourself to it. And I'll keep encouraging you in ways to learn beyond the basics, but to even to get an A in this class, you can get by learning half as much as what someone else might learn in the class. Okay, so there'll be lots of chances to go beyond the basics and keep everyone engaged. All right. Anything else I want to say about? I plan to do kind of an overview of what will be covered in the class. Yeah. So questions. If you have questions on the homeworks, the office hours with the TAs or with me. Otherwise on Canvas. We'll use Canvas as a discussion board and for announcements. So make sure I'll post then just a practice announcement on Canvas. Make sure you are getting announcements on Canvas. You're able to get on the discussions. Best to post questions there. The class the size, it doesn't scale you all emailing me. I will not be able to reply directly to emails with questions about homeworks. If it's something specific, like this project ties in perfectly with my PhD dissertation, can I do this for it? That sort of thing comes to email. A question about, I don't understand part 2A on the homework because of this, that goes on Canvas. Okay? So that's the only way it scales up. All right. Okay, and so let me switch to here. So how about we'll give most of the lectures will be on my iPad, and I'll have a few slides here and there, but I will mainly be writing stuff out on here. So, right. So I'll be writing stuff on the iPad generally. I'll have some slides which I'll annotate, but I'll mainly be kind of explaining and driving stuff as it goes, and then you have the more formal description in the notes in the book. Okay, so, but today I'm going to kind of go through stuff quickly, just an overview of everything in the class, so I'm going to have more of a slide deck that, to be honest, I haven't spent a long time making super pretty, but it contains the right content. All right, so we talked about stuff that could have been the same for a completely different class so far. I haven't told you anything about what is data mining, what will you learn in this actual class. If you took machine learning, is this the exact same class? So the answer is no. Good. Well, I designed this class so it basically was a lot of stuff that you needed to know that was not covered in the machine learning class. Okay, so is it kind of finding structure in data? Is it kind of taking machine learning and scaling this up to really large data? Kind of is this unsupervised learning? Is this large-scale computational statistics? These are all reasonable things to think of as what is data mining. I'll try and, my view is it's kind of like how to think about doing data analytics or data analysis. What's the right way to approach the problem? And this is kind of a trade-off. It's going to be a trade-off between kind of often the scale of the data and the modeling of the data. We'll talk about how do you just kind of model something as good as possible, but you need to have an algorithm that can actually kind of use that, kind of work with that model to give you something automatic. Okay? And so So some of the things we'll talk about are kind of these general principles from taking some raw and messy data that you might be starting with, or that if you're working in a company, one of the engineers dumps all this data on you, or one of the marketing people says, here's all the data I have on this, what can you tell me about it? It's usually not in the form that you see inside of the textbook when you start. Okay, and so there's some way of getting around this through like these scraping tools and parsing tools. We're not going to talk about that. We're going to talk about the principles of how to do this. Right? Whenever you get something raw, maybe it's a bunch of text, maybe it's some data sets which are annotated with text, or they're loosely put together. You're kind of losing something if you convert it into a point set or a matrix or a graph. These are all representations we'll talk about. You're losing something when you convert it into something which is the starting point of an algorithm. So we should think about, what are you losing? What are the trade-offs when you convert it into different sorts of these data types? Okay? A lot of you are computationally kind of programming, have enough ability that you'll be able to figure out how to use a scraper or something like that to do some of the dirty work. I want to teach you the principles behind it, right? What should you be thinking? And then once we have this abstract representation, kind of the starting of what your data set looks like inside the textbook, then what are the algorithms you can run on? Depending on what representation you choose, there'll be a different set of algorithms you can use. Some of them are going to be more efficient, some of them are going to reveal more structure to them. We're going to learn about these different trade-offs. Okay, so you know which algorithm to use, which one to choose. Right? If like a data mining class in another university might say, here's the scikit-learn package in Python. I'll show you how to use a bunch of the things in there. I'm not going to do that. Okay? I figure you can figure out how to read the packages and use them. I'm going to tell you what is the principle behind the algorithms in there. Those are being updated. New algorithms are coming out all the time and being added into this. The hardest decision you'll have to make is choosing which one to call. Right? So I want to explain which one has which advantages and why are there multiple things in there. I'm not going to go through all of them, but kind of the principles behind this. So if you're not using scikit-learn, you have to do this in R for a different company, right? Or you have to use a different package. You can figure out how to do it because you understand the underlying principles, the main differences underlying the different algorithms and the different techniques. Right? I'm not trying not to teach you to be a data scientist for the next 5 years, but for the next 30 or 40 years. Right? Okay, and then with these, you have to make this decision of kind of this trade-offs between scalability, how well does it model the problem, and how much error are you introducing in the process. Right? And there'll be these trade-offs, and we'll have to study kind of the interaction between these and understand where they come up. And I'll have to formally write down, how to think about these, right? Scalability, if you've taken an algorithms class, you may have a pretty good idea about this. Maybe you haven't taken an algorithms class. You'll get to see this, and I won't get too deep into the big O notation, but I'll talk about kind of, here's why this one scales and this one doesn't. And we'll see some of that on the homeworks. Right? And these other things, the notion of error in your algorithm and controlling that error is probably something you haven't seen before. Right? But this is an important aspect of data mining. Maybe 10 years ago in data mining, people didn't think about the error in your algorithm that much. Now it's kind of front and center. Right? So this is thinking about this as a first-class trade-off is kind of a fairly new development in the area. Yeah, and then modeling, we'll talk about various ways of modeling raw data into some abstract way, and then applying which algorithm on top of that. Okay, so I mean, one kind of coarse way of thinking about this is in an algorithms class, you're given a nice clean data set, and you're told specifically what to do, and you just care about doing it as fast as possible. If you're in a statistics class, one way of thinking about it, and this is again overgeneralizing on both sides, but you're just trying to model what is going on. I want to say what is the best explanation of what's going on and how do I determine that without worrying about how to extract that from the data, how to do that efficiently as the data is growing. Right? And so data mining will sit somewhere in between these two kind of areas. Right? And this is not, it's really a continuum between these different things, right? Sometimes you're gonna, I really care about modeling it correctly. Other times, I have so much data, I'm just gonna go a very basic model and just try and kind of deal with the flow as it's coming in, right? As coming in too fast to even store all the data I'm getting, what can I possibly do? Right? And so there's gonna be these trade-off between these two cases, and we'll kind of study that throughout the class. And this class probably leans a little bit towards the efficiency side of things, out of the whole world of data mining. But as data grows, that might kind of be the way it's going. So, yeah. So data mining, other universities teach, would teach this class, teach it very differently. When I first started teaching this 8 years ago, I'd say like 10% of the data mining courses were kind of similar to the way I was teaching it. Now it's, I don't know, it's hard to know. Hopefully it's over half at this point. But it's really the way it's going. A lot of this either grew out of statistics when they were starting to think about computational efficiency, or out of databases where they had really rigid structure, and the algorithms they considered were specific to that rigid structure in like in an SQL sort of database. And it's really evolved since then to do a lot more with randomized analysis and large-scale processing of more abstract and messier data. So, I mean, this class will focus on techniques that really scale with very large data sets. We'll probably have I'll try and cover a lot of stuff, but I can't cover everything. And I'll throw in what I think are kind of really cool recent developments. Usually 1 or 2 kind of newer ideas within the last 5 or 10 years within each topic. And then I'll try and formally describe the reasoning behind stuff, but there are not going to be so many proofs. Okay, so if you look at what I actually do for research and the other part of my job, I end up writing a lot of proofs about stuff in data mining. We're not going to do that, maybe I'll do 1 or 2 simple proofs in the class. That will be like a few minutes, but not too much of that. But everything will be guided from this formalism without actually going through the proofs. You can ask me about it after class. I'd be happy to tell you about these things, but I gather more than half of you probably that would be less interesting for you, so that's why I've shied away from that. And I'll try and focus on things that are not necessarily, okay, this is what everyone's kind of, this is the fanciest thing, but things that are actually kind of have found really important uses in practice somewhere. Right, so they're like, we'll see there are like 1,000 different types of clustering. I'll talk about a handful of them that are 90% of the time you should use something from that handful, as opposed to the other 995 different options, right? Even if some are flashy or in some way or the other. Okay. And so there'll be a lot of these probabilistic algorithms where you're going to use randomness inside of the algorithm. And this will kind of be a dual of what we'll think of as the data as being inherently random. At the same time, our algorithms will use randomness to kind of deal with the scale in really cool ways. And this is, again, this has been around in computer science for a few decades, but it's really found important use within data analysis in order to scale up to massive sizes. There are ways that use randomness essentially in order to do that. And we'll see a number of these things. And again, there's no specific software tool that you need to use. I recommend, if I were to choose which language, I would recommend Python. There are some parts in the back end of the class where we're dealing with more specifically linear algebra sort of stuff where like they're kind of designed, there might be more designed for MATLAB or Octave, but Python would be a good general purpose tool. But you can use anything you want, you just need to get it to work and plot stuff the way it's supposed to plot. All right, Yeah, so math probability, I mentioned those are really prerequisites. We're going to be using those a fair bit. And we're also going to be talking about high-dimensional geometry. I don't expect you to guys have taken a class in high-dimensional geometry, but we'll be talking about it, and you'll get to learn a lot about these high-dimensional geometry properties, which kind of often using the language of linear algebra to describe what data looks like. If you ever read a research paper in these areas, they write it in terms of this notation. So if you want to be a data scientist, the set of tools you're going to have is not going to be static. It's not going to stop changing after this class ends. So you're going to need to be able to read the latest research papers occasionally. You'll search for something on Google. You'll find a Stack Overflow page, say, how do I do this? They'll point you to a recent research paper, and it's going to use these ideas. And so we're going to speak in this language. So I'll try and teach you the language and the mathematical language that's used in these papers. Okay. All right, so kind of an old view of kind of data mining and machine learning is kind of this specific structure, maybe this is part of it, where your data, either you just have unlabeled data and you want to make sense of it, and so if your output is kind of, you're trying to, for every data point, you're trying to realize it as some scalar, some continuous values, and this would be, so that then this path would be doing so dimensionality reduction. And if you wanted to kind of group data that you just have, unlabeled, you're just given a bunch of data, then this is what is clustering. So I want to say these two data points are similar, and this other one is different than them. Then the first two these are in one cluster, and this one's in a different cluster over here. Right? So that would be clustering. Regression is when each data point is given some sort of label, and you're trying to fit kind of a model to all of the data, right? So you're, hopefully, a lot of you have seen some form of regression before, where you're given some sort of data, and then you want to say fit a line through this data. And what this is doing is it's given some value x here. I'm trying to predict what the value y is. So if I just have the value x, I can use my model to guess what's going on here. Right? So this is the picture of regression, and the value is the height of each data point here. That's its value. And then classification is if you've taken the machine learning class, usually you only, simplest way is you have two classes, and then I want to build a model where I say if it's on one side of the line it's a plus, the other side of the line it's a minus. So if I get a new data point, I can guess this is a minus because it's on the same side of the line as all the minuses, right? So this is kind of the basic view. And so roughly in this class, we're going to say this topic is in machine learning, and we'll try and cover everything else. Not everything else, but we'll cover these other areas, okay? And one reason I want to mention this is the one restriction I have on the project is that it's not a classification problem. Okay, otherwise everyone's going to end up just using techniques from machine learning. You can do regression, you can do clustering, dimensional reduction, other stuff we'll talk about, but I don't want you to do classification, otherwise it'll be a redux of machine learning. Okay. And so on the proposals, you'll try not to propose a classification problem. If you accidentally do, I won't take off points, but if you kind of really clearly do, and it's like, I may have to take a point or two off of there, okay? If you have a question, email me, that's fine, or come talk to me. Okay. All right, so what are we going to cover in this class? So we're going to start, and this will mainly be the lecture tomorrow on Wednesday about, that's me about, we're going to use the ideas of like hashing to kind of overview a lot of the core ideas you need to know about the probability and statistical principles of dealing with large data. And this hashing will be kind of, it's a tool which has really permeated a lot of data mining in ways you probably wouldn't have imagined. So we'll start there, even though maybe you've seen a hash table in a class before, but we'll think about this in a slightly different way. And so then we'll have a class on, or a section on similarity between objects. How do I tell if two objects are similar to each other? What does this mean? What's the difference between a similarity and a distance? And what are the computational reasons for choosing one or the other? And what are the modeling reasons for choosing one notion of distance or the other? Okay, and we'll talk about how to quickly find duplicates in large sets. Or if you have a bunch of, say you have a bunch of prior customers at a company, and you know this one was profitable, this one I lost money on, right? You have a new customer come in, and you want to guess, is this customer going to be profitable? Well, if you can find a similar customer from your database, that's a good initial guess, right, of what's going on. This comes up over and over again. This notion of similarity and how do I quickly do this is really powerful. So we'll talk about some of these issues, and hashing plays an important role here. Then we'll talk about these more traditional kind of structures in data here, where these three were inside of this box. The clustering, regression, and dimensionality reduction. Each of these will be a small section in the class. And then the link analysis will be talking about large graphs, mainly from the perspective of like a social network. Right? So on Facebook, you're friends with someone else, both are objects in the graph, and there's an edge between you. How do I make sense of this sort of structure instead? Right? This didn't fit in that diagram on the previous page, right? These graph analysis. Okay? And we'll also talk about kind of noise and uncertainty in data and some ethical issues that arise in dealing with all of this. And mixed in with these, we'll talk about some different scalability issues and models, such as your data's too big to store and it's coming in like you're sitting on a router. How do you deal with the stream of data coming in? Or your data doesn't fit on a single machine. How do you design algorithms that can work on these distributed machines? Right, so we'll mix these into these different sections when they're kind of most relevant. Okay, so let me go in a little bit more detail in each of these. So in the statistical principle, we'll kind of look at these through the idea of kind of this idea of you have this large domain, and it doesn't matter what the objects are, and I'm going to have some event that I'm going to, say, randomly put a ball into one of these bins. Okay, and you think of this could be a very large number of these objects. It could be a hash table. It could be all possible IP addresses. It could be all the words in the dictionary. And we'll think of things like as I start putting them in, when's the first time that two objects fall in the same spot? Okay. This will happen maybe earlier than you think, unless you've seen this sort of stuff before. When's the first time that I've seen every single object? About how many times do you think this happens? Okay? And then if I keep doing this, when are they all about the same? On some notion of about the same. Okay, and these are kind of key kind of properties that come up over and over again, and by thinking of this as these kind of arbitrary bins, we can kind of abstract out a lot of the kind of the different data scenarios, so we can apply these ideas to in many different places. Okay, and so we'll kind of review these principles and how these things work in one lecture, and then hopefully this kind of gives you a primer on some of the ideas which will keep coming up later on in the course. Okay. Then kind of another kind of group of kind of a theme that we'll start on next. So this will start next week already. So we'll have some sort of messy data, and we'll start with just a string of text, okay, or just a document of text. And the goal is, like, I want to say I have one document. I want to find another document which is similar to that document. Two news articles where they're on the same topic, or two homework assignments where someone copied from someone else. Okay, so that these are very practical things. And so in order to do that, just looking at the strings of text, this is not a natural language processing course. I'm not going to try and attempt to actually understand the meaning of these things. I want to kind of use the patterns of language to convert these into something easier to work with, that I could then look up and say the right algorithms textbook or the right Daemine textbook and apply a known technique. And so we'll convert text into things like sets and to things like points, high-dimensional points, okay? And these abstract classes, either a set from some domain or a point in some dimensional space, these will be more natural to define similarities and distances between, and then we can talk about those differences between. And so this will be common throughout the class. When we talk about graphs, we'll actually think of converting them into a matrix, and we'll often think of either the matrix or elements of the matrix again as point sets. So we can then think of them in terms of distances in more intuitive ways, right? And if we think about a bunch of customers in a database or some sort of database you have, again, we want to somehow think about these as point sets. And so this kind of theme comes up over and over again. We want to kind of think of each object. Bob here becomes this red point, right? And Sue becomes the blue point, and they're closer to each other than they are to Joe, who's the black point, right? I want to somehow create this representation for this to make sense. And then once I'm here, I want to know what can I do efficiently with high-dimensional data points, right? So this will be the first longer section of the class starting next week, kind of how to deal with a lot of these conversions. And once I have them as point sets or sets, what can I do with them efficiently? Okay, so yeah, so one question is similarity. Given a query, which one of the points is most similar? And are there 2 points which are basically right on top of each other? Or something like that. Okay, so then the next module will be on clustering. I mentioned a little bit what this is, but it's kind of, you're somehow given some data points and you want to determine which ones are similar to each other. And there's this enormous literature, countless variations on this. We'll talk about 3 different types. Hierarchical clustering, which is, you often think of this single link clustering, which kind of connects them as a graph in the simplest way possible. And if they're connected, they're in the same grouping. So k-means clustering in general, center-based clustering, where I assign some representative and I map every point to the closest one. And spectral clustering, which first models it as a graph and then keeps cutting the graph in half. And each time it's in half, those sides are, so I'm building a hierarchy, and when I stop cutting, what's left is in one cluster. Okay, so these are the basic ideas, but we'll kind of go through what's behind them, when they work, how efficient are they, not just what is k-means clustering, but what are the kind of the other just as simple things that you may not know about, which are just as effective. So yeah, and so these pictures, okay, so we'll come back to this when we get to the section, but these pictures are incredibly deceiving in that I'm showing you these data points on the board in 2 dimensions, and if your data ever looks like that, you can just print them out on paper, take out a marker, and circle the groups of stuff together. Okay? So really that's going to be the best thing to do if your data looks like this. And you can automate it with these things, but you're going to be more sure of your results if you do it that way. Okay, so all the algorithms we talk about are going to extend more generally than that to data that I cannot visualize so easily. And that's where these really gain power. Okay, so this seems really easy when I describe it this way, but you want to describe in the right language so you understand how they generalize. And we'll talk about a bunch of different similarities and distances in the previous section, because that'll be a choice that goes into how the clustering works. We're going to use a distance that we define between 2 data points, and then we don't need to know what this picture looks like. We can just rely on the distance to tell us. Right? So that ends up being really important. The next section will be on like regression. So how many people have seen least squares regression in a previous course? And how many have not seen it in a course before? Okay, good, good. So I'll spend about 10 minutes covering it, and then we'll move on to other things. We'll kind of review very quickly how to do polynomial and high dimensional regression and simpler things. But then we'll talk about like the non-optimality or the optimality and when that's broken of least squares of least squares regression. We'll talk about how to create models on high dimensional data which forces it to be sparse and simple. Right? So I'll start with least squares regression, which is really the central idea here, and we're going to add stuff onto it. That's going to have other forces here. We'll think about the least squares regression model has a very simple and closed form algorithm. Some of these other ones don't. Some of them do. Right? We're going to look at what is available in space. Right? And one kind of, I think, cool thing we'll look at is this idea of compressed sensing. When you have a huge number of variables and you want to fit a very simple model, and if you make some assumptions on the simplicity of the model, and the data actually comes from that with noise, you can recover it exactly. Okay, and there's some very kind of cool developments in here that move beyond the simple ordinary least squares, and so that's what we'll cover within this course. Okay, so the next section will be on dimensionality reduction. Okay, and this is where I'm going to start. Again, this, if you remember from that table, this is unlabeled but data set, but in this case it'll be very high dimensional. And my goal is to find a much lower dimensional subspace that is going to capture this data well. So I say I don't really need all those dimensions, and even without knowing the labels, like I did for regression, here this only worked if I had a label, and everything is about trying to preserve the prediction of this label. In dimensional reduction, I don't have this to aid me. So I just want to keep as much structure as possible using in this data without knowing anything about the label. Okay, and so kind of you can think of these, kind of the only picture you can really draw is you have, say, 3 points here and you fit a one-dimensional line to them. This is almost too perfect. In general, the workhorse here, one of them will be the singular value, so decomposition. And if you haven't seen this relationship to data, this really encodes a lot of structure about the dimensionality, in some sense optimal dimensionality reduction of the data. So we'll start there, and how this relates to principal component analysis and some other ideas. And we'll talk about other things as well, such as multidimensional scaling. So how do you learn a good distance function using these ideas? So if I want to learn a distance function between the points, how do I do that using the underlying structure? Right, one that is somehow preserving some labels a few labels I do know about the data points. How do I then create a good distance between them? And then we'll talk about some very large scale, kind of how to do this in a stream or these other kind of distributed settings using these ideas called so-called matrix sketching. So thinking of your data set as a matrix, a very large matrix, turns out to be a really powerful abstraction. And so a lot of techniques in data analysis and machine learning will do some stuff we've talked about earlier in this class by the time we get here, and you'll have your data as a large matrix. But this has become popular, but these matrices have gotten really large and very hard to deal with. And so matrix sketching is a way to deal with them very efficiently. Like reading over the data once is enough. As fast as reading the data, you can get a good dimensionality reduction that may preserve even properties of regression or other things that you might want. So we'll talk about how to do these and look at ideas like random projections, which are kind of orthogonal to singular value decomposition. That wasn't It wasn't intentionally a pun. But, okay, good. A few people got it. Maybe it was a little intentional. Okay, okay good. So if you didn't get it yet, you should get it when we get to this part of the course. So I probably won't be able to resist, and we'll tell it to you again. Okay, so this is a warning about that. Okay. So one thing that's going to permeate the kind of a lot of these discussions, but we won't be able to talk about until later on in the semester, is like how to kind of abstractly think about the ideas of noise and uncertainty in the data. So I mean, you could start with a class in statistics where this is like the first thing you talk about, right? I think we're going to talk about this in the context of building a model or finding structure in the data. And so I think this will make a lot of sense from the data mining perspective once we've gotten to this later on in the semester. We'll talk about what is noise, what are outliers, how to deal with them, and kind of some ideas of privacy that comes from, hey, if you add noise into the data the right way, you preserve the structure, but you've kind of somewhat anonymized the data. There's some kind of ideas around called differential privacy that talk about how to formalize these ideas. We'll talk about some ethical issues with this sort of stuff as well. Okay. And then the final section of the course will be on these link analysis and graphs. And kind of one of the main things I want to talk about that kind of fits in well with the rest of the class is this is going to be this PageRank algorithm. So who's heard of PageRank? And so anyone not heard of it? Okay, so this is the algorithm that kind of made Google able to beat all the other all the other search engines. So there's in early 2000s there were a handful of search engines, and if any of you remember from back then, they weren't all that good. And then Google came from a couple of PhD students from Stanford with this PageRank idea, and it basically cleaned everything up by understanding the structure of the web graph and using that in a way that's effective. And this will tie in with a lot of the other kind of thinking of data as a matrix ideas. And so to get there, we'll have to first talk about what are our markup chains on a graph. And we'll relate this to other ways you may have seen markup chains before. Say if you've taken a probabilistic modeling class or a computational Bayesian statistics class, they usually think about the same markup chains but in a very different settings. And we'll kind of blend these together. And then we'll talk about, this is where I'll talk about MapReduce a little bit and kind of these distributed clustering ideas, because this came around essentially partially because of PageRank and related things. And we'll talk a little bit about finding communities in graphs. If you use a social network, how do I determine a subset of the nodes, of the users in it, which are more similar to each other? And we'll kind of go through some topics in this area quickly. Okay, and then quickly I'll mention, sometime we'll talk about these like streaming algorithms where the data is so big that you can't fit it, you can't store all of it. What kind of summaries can you keep? And in this case, you'll have to do something even simpler. I'll just be able to keep approximate counts of various things, for instance. And we'll talk about various of these. These will be a few lectures mixed in various spots as well. So overall, I think this will be, I think it'll be a very fun semester. We'll get to talk about stuff that I think is really cool. And it'll hopefully give you a big intuition for what is data analytics and what are the challenges with it and how to kind of think formally about this. How to model your data into different abstract types and how to kind of trade this off with various efficient techniques. When can I make this efficient and when can I not? All right, so I'll stop here for today and we'll jump into kind of a pretty big lecture on statistical principles on Wednesday. And the first homework is out. Take a look at it. It will make sense after class on Wednesday.